Do you see?
Yes, we would request you to go full screen.
Full screen. Oh, I don't see where I should do that. Jeff, full screen now?
Yeah, it's full screen now. Perfect.
Oh, but we have to go back.
Could you go back to the slides? Just test that. Oh, lovely. Yeah. Okay. Excellent. Thank you. So,
okay. So, so maybe
we have the chair for your session, Professor Sanjay Jain, and so we are now waiting for some audience. So, yeah. So we'll begin in about 5 minutes as per schedule.
Okay. So I just keep it up. Then I know it's working.
Yes. Please keep it up.
Yes.
I'm Sanjay Jain.
Okay.
Hello.
Thank you.
Sanjay da, pranam. Hello, Sanjay da.
Hello, Gargi.
So lovely to see you, Sanjay da.
Yeah, it's been great to be participating in this meeting.
Oh, it's our honor. It's so overwhelmed to see you and Nivedita Di today.
Yes, right. It's been listening to what people have to say about in the Delhi University condolence meeting, we had a smaller number, a set of people of more locally, but here we have a large number of people participating. Very nice.
So true.
I'm very glad that something like this is happening.
Absolutely. Indranil is there also. Professor Jutta Kunz is there. She's joined. I think she's already there.
Nice to see you.
I can see. Because some people are on, but you can't see them. Some people are. Indranil is there.
Yes.
Hi.
Lovely talk, Indranil.
Thank you.
Yes, I enjoyed your talk very much. I learned a lot from it.
I didn't understand, but my problem is that my phone, I'm having to do it on my phone and I can't keep it very close. My eyes I'm having a little problem. So I'll have to even, Professor Haridas is there. Okay. Now I'll just okay, here. I think it's time.
It's 3:28 according to my my
Yes.
watch.
Closing.
And we have 5 speakers in the session, and let's see. Professor Kunz, then Professor Kulshresht, then Professor Patrick Dasgupta, whose talk will be relayed by Professor Alok Mishra in the form of video, and then Professor J.D. Anand, and then Professor Dadhich. So, Professor Kulshresht, I think, has also joined the meeting.
Yes, Sanjay, I'm very much there.
Hello.
Yes.
Okay. So,
Is that right? Yes.
yes. I will, so everyone has a total of 30 minutes. And at sometime between 20 and 25 minutes, I will let you know how much time remains out of 30.
Sanjay, I would suggest that I would finish in 30 minutes. So you don't need to bother. Well, maybe 2 minutes before 30.
Okay. I will do that. Yeah, and it's now 3:30. So, Professor Alok Mishra, should we start now, or should we wait for another minute or so?
I leave it entirely to you, Professor Jain. It's your call.
Okay. I think Professor Jaidev Anand has also joined. So effectively, since Professor Patrick Dasgupta's talk you have, I think 4 of the 5 speakers have joined in some sense. And so I think perhaps it's time to start because we have another session after this one. And this being a long session, we'd like to give people some time before that. I'm very grateful to the organizers, Professor Alok Mishra and Gargi, and Professor Alok Mishra's team for organizing this and giving me the opportunity to chair this session. Very briefly, a lot has been said about Professor Mitra. I should mention, and there's just one thing that I'd like to elaborate upon, which has been touched upon, but it has affected me very much. So I'd just like to mention that I was an MSc student in the Department of Physics during 1979 and to 81. And then later on, I was a faculty from 2002 onwards. I was taught quantum mechanics during my MSc days by Professor Mitra in my first year of MSc. And the thing that had a great impact on me, one of the things, among other things, is his passion for physics. Okay, till my first year in MSc, I had never encountered someone who was so deeply passionate about and immersed in physics. Okay. This was evident from the way he taught. Okay, he derived things from scratch, from first principles. It was evident from his gestures, from his tone of voice, and his, his childlike joy at reaching some point in the lecture and explaining things to us. You could see that he very deeply felt the beauty of the subject. And the fact that quantum mechanics has exposed something so unexpected and profound about the universe, which he wanted to communicate to us. His lectures, this interaction reinforced the feeling that physics was the to confront the greatest mysteries of the universe, and that it would be deeply rewarding for me personally to pursue it. And I'm very fortunate to have had that inspiration. And later on in my career also, his affection and concern for me have been very valuable. So with this brief, perhaps not so brief, remarks, I would like to start the session and welcome Professor Jutta Kunz to give her talk on the ring down of rotating black holes.
Yeah,
sequence.
thank you very much for this very nice introduction. And thank you so much also for the invitation to this really nice conference. It's an honor for me and a pleasure, of course, to participate in this meeting. I myself think I only had once in my life the opportunity to meet Professor Mitra when we had this meeting 2013 in Delhi, organized by the nuclear physics group and my friends Usha and Jaya Gulshraj. So now with this session, I think we switch a bit from the nuclear physics to the gravity, and we did have already a little bit in the first lecture of this conference on the ringing of black holes, but now I'll talk a bit more about it, and in particular I'll go to rotating black holes. And no, it doesn't work. It did work all the time, and now it works. I would like to give you the outline after an introduction, and it'll be a little longer because it's now switching topics to gravity. Then I'll talk about a specific type of black hole and about the ring down and testing Einstein's general relativity, and then I'll end. Now, here you see the beautiful Einstein equations, and on the left-hand side you have the gravitational part, the curvature, which is what or how Einstein describes gravity, and on the right-hand side you have the energy momentum tensor. So you have a rather complicated looking set of equations already for general relativity. It's nonlinear partial differential equations that need to be solved. But Karl Schwarzschild, this German astronomer, he immediately realized that if he gives sufficient symmetry to the problem, he can find a solution, and he was interested in describing the solar system. So he assumed that the space-time is static and that it's spherically symmetric, which is a wonderful approximation for our solar system outside the sun. But then when one looks at the whole solution and also allows for the inside, so does not look at the matter of the sun, then one arrives at this surprise, namely one finds the first black hole of general relativity, the Schwarzschild black hole, the famous static spherically symmetric black hole. And it's really very simple. It's given by a single quantity, basically the mass. The mass determines the event horizon, and inside it has a singularity. Now, when we look at our universe, almost everything is rotating, right? The Earth is rotating, the sun is rotating, and the stars. So one is expecting if there would be black holes in the universe, they would be rotating. And so we have to generalize the Schwarzschild black hole to a rotating black hole. And this was done by Roy Kerr almost 50 years after the Schwarzschild solution was found. And it's been believed and beautifully expressed by Chandrasekhar that this myriad of black holes that is residing in the universe is probably, at least to a high degree, described by Kerr black holes. So these Kerr black holes, they are now stationary, and they are only axisymmetric. They are rotating, so they have some deformation, and they have this funny surprising property called ergospheres. So within this region here in the figure, you see it as green. within this region, everything has to rotate along with the black hole. And inside the singularity is now no longer point-like, but ring-like. But let's forget about the inside. We are interested in the outside and our universe in the observable part. And still, these Kerr black holes, they are very, very simple. They have an enormously high degree of symmetry, and they are characterized by just two numbers, by the mass and the spin. And so Wheeler said black holes have no hair, because that's all you need to know, the mass and the spin, and then you have the whole space-time. And they have even some hidden symmetry, which is very, very helpful in general relativity when studying black holes and their properties. So we have what is called the Kerr paradigm, saying that most probably all the black holes in the universe are very well described by the Kerr black hole solution. But maybe there are some deviations. And this means we would like to test gravity. We would like to test general relativity. And yeah, there's various reasons to think that general relativity is going to be superseded by some other more deeper going theory of gravity, including quantum mechanics somehow. And so when it's looking for tests, and also, of course, from the cosmology side, we know there's all this dark part of the universe, the dark matter, the dark energy. So maybe we can describe the whole thing in a more comprehensive way. And so we are looking for testing the Kerr paradigm, testing general relativity. And very nice tests are now available to us. Namely, we can watch the gravitational waves that are emitted when these objects, black holes or neutron stars or mixed systems, when they inspiral and then merge and then ring down. So we have these three phases of such a merger event. And in this talk, I will focus on the last, namely the ring down, and see what type of deviations might we expect by looking at theories beyond general relativity. So this will be mainly what I'll be talking about, but there's of course other tests, and one also very nice is done by looking at the shadow. The Event Horizon Telescope collaboration has obtained these beautiful images of the black holes in M87 and in our Milky Way. And yeah, for both, for gravitation wave tests and for these tests of the shadow, general relativity does perfectly so far. However, if we have future observations, more accurate observations, possibly one might find some deviations and then get some hints towards how some deeper theory of gravity might look like. So when we're going to such a theory, of course, whatever theory of gravity one is thinking of, one does have to respect what is known, namely solar system tests. Everything that is known in the solar system must be satisfied by any viable alternative theory of gravity. But in the strong gravity sector, where we have black holes, where we have neutron stars, and possibly some exotic compact objects, in the next talk, will address some exotic compact objects like boson stars. So there's still some freedom, and so there we would like to find constraints. So now let me focus on one specific theory which we have studied a lot and other people have studied a lot. And this is called Einstein scalar Gauss-Bonnet type of theories. Here you see the action, and this first piece here, this is just the Einstein-Hilbert action. And then this last piece, this is called the Gauss-Bonnet term. It's a term that is quadratic in curvature. And here you see how it looks like. And this is the first term that actually arises when you go to higher dimensions. So the first Lovelock term. And Naresh Dadic is very fond of these, will be the last speaker of our session. And in 4 dimensions, this term by itself does not contribute. However, if it's coupled to a scalar field, and here you see some coupling function to some scalar field phi, then it does contribute, and we obtain this set of theories, the Einstein scalar Gauss-Bonnet theories. And they are quite nice from various points of view. For instance, such types of theories arise when you look at the low energy effective action as you obtain it from string theory, or when you do some effective field theory expansion in the derivatives of the metric. So these terms always arise here. Of course, we use special coefficients, but the Gauss-Bonnet term arises in string theory, but then coupled to a special scalar field, the so-called dilaton. So one has some theoretical motivations to study quadratic curvature corrections to general relativity. And this way, with the Gauss-Bonnet term, this is particularly nice because one obtains a set of second-order differential equations, and this is what one is used to from Einstein's theory. So let's now look at the black holes that arise in this theory. And the first papers you see here, 95, 96, are quite old. And the motivation at the time was basically string theory. And so the coupling function was taken to be a dilatonic coupling function, which means you have some exponential coupling to the scalar. And alpha is taken to be a free coupling constant. And then for this theory, the static black holes were obtained. And here you see in this figure, the horizon radius versus the mass. And it's scaled by the coupling constant. And of course, for Schwarzschild, you just obtain a straight line. But when you now look at the black holes of Einstein dilaton Gauss-Bonnet theory, then there's a dilaton. So these black holes have hair. They have a scalar field, and this scalar field gets more important the bigger this coupling constant is. And for very small coupling constants, in the limit coupling constant to 0, you just go to Schwarzschild. And here you see up here towards this corner, you go to Schwarzschild. But then you see all of a sudden here, funny, the solutions stop. You don't go all the way to 0, but there's a minimal mass or a maximal value of the coupling constant for a given mass. So one has a critical solution, and in this type of theory, there's always some radicand that vanishes when one looks at expansions. And so this is right where the solutions stop, and we call them critical solutions, where you cannot follow to smaller masses anymore, or larger coupling constants. Now, of course, we want rotation, right? So we have to rotate the black holes. And here we have the horizon area versus the angular momentum, both scaled in some way with the mass. And the static solutions we just looked at are residing here on the axis, and this dot corresponds to the critical solution. Up here, the black curve corresponds to the Kerr black holes, and whatever is shaded, you see, these are all the possible black holes that you have in this theory. So you have a whole domain of existence for such black holes, and the horizon size can be quite a bit smaller. And also very interesting, for Kerr black holes, you have a maximum of the angular momentum, which is 1 when you scale it by the mass squared. But here, no. You can go a little beyond. This is the same plot, let's say now, for the angular momentum versus the coupling constant, just to kind of point out again that you cannot go to too big coupling constants. Then there's just no more solutions in this type of theory. When you look at the shadow, unfortunately, you don't see much. It's not expected to be observable that you have such a small difference also with the next, I would say, a generation of instruments, but there might be a possibility of making observations by going to gravitational waves. So there may be differences as compared to the Kerr black holes, because one has the scalar field present. A scalar field also allows for radiation that is lower than quadrupole, right? We can have dipole radiation, for instance. And so the coupling of the scalar with the gravitational field of the background solution is also producing some coupling in the equations, and so one expects some real effects if the coupling constant isn't too small. Of course, going to 0, you don't see anything because you go back to Kerr. So now let's look at the in-spiral phase and not the in-spiral phase, the ring down phase. So let's first look just at this last piece after the merger, how this highly excited black hole rings down to its final state. And how do you do this? Now, you do some perturbation theory, you perturb around this hairy black hole. So you have perturbations of the metric and of the scalar field, and you can classify them into even parity and odd parity perturbations. And when you look at static spherically symmetric black holes, this is quite doable. You obtain some master equation, some Schrödinger-like equation for the eigenvalue, and the eigenvalue, because you have damped oscillations in the ring down, has a real part and an imaginary part. The real part corresponds to the frequency, and the imaginary part to the decay time. So this is what one finds for the static black holes. And here you see the real part scaled with respect to Schwarzschild, and the imaginary part scaled with respect to Schwarzschild. And we start here at 1 because it's scaled with respect to Schwarzschild, and then we increase the coupling constant, and you see for large coupling constants, a lot of things are happening. So one obtains really deviations in the frequency and in the imaginary part. These are the axial modes, quadrupole axial modes. These are the polar axial modes. You see the scalar and the gravitational-led modes that kind of go to different directions here. But we really want to look now at the rotating modes, and I don't have too much time left. So let's now focus on the rotating modes. For Kerr, this has been done. And there's this very famous Tchaikovsky equation. And because of the very high symmetry of the Kerr black hole, one still gets some decoupling of the radial coordinate and the polar coordinate. For some general black hole, rotating black hole of whatever generalized gravity theory, this isn't happening. These black holes are too complicated. They don't have this high underlying symmetry. So in that case, one simply has to use, let's say, brute force. One has to discretize and use some spectral method or other method to solve a complicated coupled set of equations for these modes to obtain the eigenvalues. And that's the quasi-normal modes. So we have, together with our colleagues in Madrid, Jose Vasquez Salcedo and Fichsenko and Francisco Navarro Lerida, and also Luis Manuel Gonzalez Romero. With them, we have developed some methods, some spectral decomposition using Chebyshev polynomials, Legendre functions, and we have tested it on the Kerr quasi-normal modes. This is a piece of the Kerr spectrum where you have the different L going in this direction and the overtones going in this direction, and we can get perfect agreement up to a number of digits. And so we were confident of applying this procedure to our first set of black holes, rotating black holes of some alternative gravity theory. And here you see small angular momentum still. So there we could also compare with perturbative calculations for perturbation and angular momentum, and we also agreed. And here you see on the left-hand side the frequency, on the right-hand side the imaginary part, and the most important modes are those that live the longest. So it's those, that are high up here. And you see for a general relativity, we have the quadrupole modes, and we have degeneracy of axial and polar modes, isospectrality. And then there's the splitting arising. So isospectrality is broken. And very interesting, as we go to very large coupling constants, then we see also the order of the modes. What is the most important mode? This is changing. And I must say, it came as a real surprise to us that, as you can see here, it's the scalar-led mode that is coming up and becomes the most important, the leading mode in this case. And we have done this for higher angular momenta.
Professor Kunz, you have 5 minutes.
5 minutes. Oh, I thought I have to be faster. Thank you. So we have studied this for a variety of modes, seeing how important it is to take all these modes into account and making some predictions. And we were hoping we would be able then to, with future observations, future gravitational wave observatories, be able to make some distinctions between the different modes there, and then be able to put some limits on this type of theory from gravitational waves. But actually, it turned out, basically at the same time when we were doing our calculations, colleagues in Potsdam did calculations of the full thing in some approximation, but they did also the in-spiral. And from this in-spiral, you obtain already now the best current bound on the coupling constant, so on this theory. Namely, here you see the ring down starting at some point with the same kind of starting conditions, initial conditions, and then the system is evolved with in general relativity in red, then light blue, some intermediate value of the Gauss-Bonnet coupling constant, and dark blue, some high value of the Gauss-Bonnet coupling constant. Yeah, it's normalized differently from what you saw before. But then, I mean, the main effect you can see here down in this diagram, you see the red curve ends here at 0. But as the Gauss-Bonnet coupling is increased, the merger, this ring down, the end spiral, it's basically the end spiral phase, this happens faster. So this end spiral phase then, yeah, this has additional radiation. It does not only have the quadrupole radiation, but we have a scalar, so there's also dipole radiation, and it's basically an effect of this dipole radiation that we see here, as these colleagues say. So there's the best bound currently on this type of theory from gravitational waves, but from the in-spiral phase. Now let me come to the conclusions. We have seen that the Kerr black holes after relativity have a very high degree of symmetry, and so they are very well to handle because of that symmetry, and basically everything has been done, and lots of things you can do analytically for them. But this whole merger process has been done by numerical relativity because the merger itself is too complicated to handle in whatever approximations. Now, when you go to theories beyond general relativity, and we would like to see some deviations somewhere, hopefully, giving us some direction where to look for. And then black holes can be much more complicated. They can possess hair. And this is now what many people in the community are doing, looking at theories that go beyond Einstein and try to look for observational signatures that might be possibly detected in the future. Thank you.
Okay, thank you very much, Professor Kunz, for that very clear signal, of beyond Einstein gravity in the ring down of black holes. We have time for a question or so. We are one, perhaps maybe two questions if they're brief. I see, just a second, Alok, Professor Alok Mishra, I can see your hand. Please.
Yeah, sorry, I just had a quick question. This is something which has always puzzled me. I mean, I don't work in this area, but I mean, when we're after all talking about a black hole merger, so what baffles me is how come first order black hole perturbation theory would suffice? I mean, I also remember coming across some Fitzgerald Leonard's paper a couple of years ago where they go up to second order, but I mean, I feel that this should be entirely non-perturbative in gravity. I mean, this should be this should be not addressable within the confines of linear perturbation theory. Maybe I'm wrong. I'm missing something big.
Yeah, I mean, in this area here, this is where one is using basically the full numerical relativity, no perturbation theory, just solving the full set of equations, because whatever approximations you use don't suffice. You have to use the full thing. So, but these numerical relativity calculations are very long calculations. And so one is still trying, because one cannot do them for all kinds of theories. One is still trying to obtain information. And here in the ring down, yeah, one has a chance to obtain deviations, because yeah, it's at some point, and it's not quite clear when, this being under debate, where you should start fitting the quasi-normal modes. You might get then information just and bounce on the theories just by using this perturbation theory. And also in the in-spiral, yeah, approximations can be used to go there, post-Newtonian to, I don't know, third, fourth order are being used here.
All right, thank you.
Okay, thank you very much. I think we should move on to our next speaker, Professor Dayashankar Kulshresht, who's a senior colleague of mine. I'm happy to welcome him for his talk on boson stars.
Thank you, Sanjay. Thank you very much for your very kind words. And then let me first extend my heartfelt thanks to my friend Alok Mitra and his tech team for doing a very, very wonderful job on this for this meeting. Today is the birthday of my Guruji, Professor A.N. Mitra. I would say only half a line that Professor Mitra was very, very fond of me. And he would love to have a cup of tea or coffee with me, depending upon if he were in the department. At home, he would usually make the coffee himself, insist on making it himself. So with that, let me share my screen. Sanjay, could I share my screen?
Absolutely, absolutely. The floor is yours.
Okay. So all right. So with those words, let me then start on the topic of my talk. And one of my collaborators, my kind of guide and mentor in this particular field is Professor Yuta Kun, who happens to be here already. My other collaborators are Sanjeev Kumar, Usha Kulshrestha, of course, Yuta Kun, Sarah Kallen from Oldenburg, and Sushil Arora. And this talk is based on a series of publications beginning with 2014. So classical and quantum gravity, general relativity and gravitation, physical review D, rapid communication, physical review D, regular physics letters B, few body systems, European Physical Journal C, and this wait a minute. Oh, something went wrong. Let me just have a I'm sorry for the interruption. And maybe I made some mistake.
We can see your slides. We can see your slides. Perhaps the next slide is
I'm not able to see my slides myself. Can you help me?
Professor Kusheshwar, would you want me to share your slides, which you had already shared with me?
No. I would do it myself. Otherwise, I would be lost. So, okay.
This meeting is being recorded.
Is this okay? So thank you. I'm sorry for the interruption. Is this all right, Sanjay?
Yes, we can see your slide. Yeah, we can see the next one as well.
Okay.
We can see slide number 2.
Okay. So let me start.
Professor Kusheshwar, apologize to interrupt you again. Since you're logged in on 2 devices, there is an echo. So we cannot hear you.
I'm noticing. Did I join it from 2 places? Yeah, yes. I think. Could I stop and then again share? Wait. And
You need to mute one of the devices.
is this okay now? This looks all right.
This is fine. There's
There
no echo
no
now.
longer echo, yes?
Yeah, no echo, and we can see your slide.
Okay, fine. Thank you. Sorry for the interruption. So, in this, I still need to change the view because it is interrupting my Usha, can you help me with my?
You want to go to slideshow?
No, this my photos were blocking this. No, I want to go to side by side. Yes, okay. But then this it covers my. Okay, all right. So I'm going to present in this talk. I'm sorry, I lost a few minutes. In this talk, I'm going to present a few field theoretical models of boson stars and the field theoretical models of complex scalar fields coupled with gravity provide the non-singular asymptotically flat solutions which are referred to as the boson stars, which are the gravitational bound states of scalar particles. In general relativity, a non-singular asymptotically flat solution refers to a solution that describes a space-time which is free from all singularities, that is, no points of infinite curvature at any point, while still exhibiting the property of being asymptotically free. So it means that geometry approaches the flat space-time of special relativity at very large distances. At very large distances from the source of gravity. Boson stars are hypothetical astronomical objects that consist of particles called bosons. Scalar fields occur routinely in particle physics, field theory, gravity theory, string theory, and cosmology. And scalar fields interacting with gravity through a gravitational condensation mechanism might form spherically symmetric objects, the boson stars, that would be stopped from collapsing by Heisenberg uncertainty principle. The boson stars were conceived almost half a century ago, and they are very interesting from theoretical point of view. Their potential astrophysical applications are of wide interest. Accretion disks around boson stars have been studied. Gravitational wave signatures of boson stars have been studied. Binary systems of boson stars have been studied. Discovery of hairy black holes based on boson stars have been studied. And it has also been discovered that rotating boson stars allow for static orbits. So Olden Group, led by none other than Professor Yuta Kunj, has been at the forefront of many of these studies. And just like supermassive black holes, boson stars could exist even at the center of galaxies and could possibly explain many of the observed properties of active galactic core. Boson stars could have been formed, for example, through gravitational collapse during the primordial stages of the Big Bang. It may be possible to detect them by the gravitational radiation emitted by a pair of co-orbiting boson stars. Gravitational lensing by boson stars has also been studied, and they have also been proposed as the dark matter candidates. They have also found applications based on the ADS-CFT conjecture. Amongst the important properties of boson stars, their mass, their size, and their particle number, which is proportional to their charge, are of great interest. Particle number of boson stars arises from the U1 symmetry of the underlying theory, which gives rise to the conserved current and the associated charge. Also, when U1 symmetry is made a local symmetry, charged boson stars arise. So I will be presenting three models. Two of them will have local gauge symmetry, and the other last one would have a U1 phase symmetry. So they will not be charged, but the first two ones would be the charged boson stars. So boson star solutions could in principle be obtained by employing any self-interaction scalar field potential. And these theories are interesting because they are perfectly well behaved from physical point of view, and they lead to compactness of solutions. Here, compact is meant to describe a solution whose scalar field vanishes identically outside a compact region of space. Oldenburg group in particular has made extensive studies of boson star solutions and concluded that the compact boson stars arise when a V-shaped conical self-interaction potential is employed. The boson stars in a theory without a conical potential do not feature sharp boundaries. In compact boson stars, scalar field is completely confined to a finite region of space. Now, also, boson star solutions do not exist for arbitrary values of the parameters. They exist only for a certain domain of the parameters. In our work, we first obtain the domain of existence of the parameters of the theory for which boson star solutions exist, and then study the various properties of the boson star solutions. Now, let me come to the first model, which is described by this action. So you have the Ricci scalar R and the cosmological constant lambda and the matter field Lagrangian, and this is the minimal coupling term. So U1 gauge field, kinetic energy, and the complex scalar field. And this is the potential. So this is a model of massive scalar fields, and this is a conical potential. Now, in this conventions, when lambda is positive, then it's a de Sitter space, and when lambda is negative, it's anti-de Sitter space. So the usual procedure, variational principle, gives rise to the equations of motion. The first one is the Einstein equation, Maxwell's equation, and then the Klein-Gordon equations and its complex conjugate. Of course, they are coupled nonlinear differential equations, and this last one is just the energy momentum tensor. So we assume that A and N, the metric functions that appear in the definition of the line element or the metric tensor, are functions of R only, not of T, theta, and phi. And so for spherically symmetric solutions, we adopt a static spherically symmetric metric with Saussure-like coordinates given by this. Now then, making use of the conventional definitions of the Christoffel symbol, Ricci tensor, and Ricci scalar, etc. As you will see, all of them, they can be derived from this J mu nu. And so eventually here they are functions of A and N and their derivatives. So the Einstein equation, this is the Einstein tensor, and this is the Einstein equation, in the component form can be written like this: T, R, theta, theta, phi. The last two equations yield identical results. An important ansatz that we make for the matter fields is phi expressed in terms of this, and A mu dx mu is AT R dt. So we work under the assumption of vanishing electromagnetic field, which implies divergence of A equals to 0. This leaves us only with time-like component of A mu. Space-like components of A mu do not contribute in this assumption. Now, you see, in this theory, we have some constant parameters which are dimension full, and the field variables H and B are also dimension full. A and N are dimensionless. So we construct new variables. So we define new constant parameters in terms of the old ones. So the new ones are dimensionless. And the field variables are also defined, reconstructed, so that this H and B are dimensionless. Then we also like to make the argument of the fields to be dimensionless. So we define r hat equal to mr. And with this, these are the new definitions of the scalar matter field and the vector matter field with dimensionless arguments. So this eventually the equations of motion, they reduce into this set of 4 equations. This is scalar matter field for the U1 gauge field and for the metric function. So these are, they are obtained from the Einstein equations. Then you choose the appropriate set of boundary conditions and for the boson stars and for the boson cells. So here, of course, the outer region, the boson stars, we match the exterior region outside the boson stars with RNDS or ADS solutions. And in the boson cells, we match the interior region R less than Ri and the exterior region R greater than R0 with the appropriate RNDS or ADS solutions. So the U1 invariance of the theory would lead to the conserved Noether current and the corresponding charge density and the global charge Q. And the mass parameter M of the theory is given like that. So then I'm going to present some phase diagrams. And this here I like to explain that in our studies of the phase diagrams of boson stars, we find that a passage from one set of phase trajectories to another occurs suddenly or catastrophically. In the bifurcation phenomenon, when a sudden change in the behavior of the phase trajectories occurs as a parameter passes through a critical value, then the phase point corresponding to that critical value of the parameter is called a bifurcation point. In our model that we consider, we obtain up to 4 bifurcation points. However, in the entire series of papers, we eventually establish that an infinite sequence of bifurcation points exists in the phase diagram of the boson stars. Also, if a system contains more than one parameter, then each parameter has its own bifurcation points. Now, let me show some results. So this is very important result. This is a scalar field at the center of the star. This is the vector field at the center of the star. And let me recap that when we started working or picking up this field from my collaborator, Professor Yuta Kunj at the University of Oldenburg, she already had, this was around 2010, she and her group, they had discovered this particular bifurcation point when we started working on this project. And you see here, these are the in the region 1A and 1B, there are some phase trajectories. And when the parameter lambda, the cosmological constant, passes through this particular value, then they immediately change from, they now appear in the region 2A and 2B. So there is a sudden change, you see, from 1A, 1B, now they disappear in those A domains and they appear here. So around 2010, when Sanjeev passed out his master's degree, he was keen on working with us. And we had picked up some of the basics of this work from Utah at Oldenburg. So I suggested to Sanjeev that if it interested him, he should work on this. And he liked the idea very much. And then he worked for some time to develop his own computer program, which today is a rather $1 million computer code or computer program where his numerical accuracy is very, very accurate, up to several digits. So you see here, this portion is being blown up here to show more bifurcation points, 3, 4, and so on. 1 and 2 are visible here. This is another set of phase space variables, A0, metric function, and the vector field. So then this is A0 versus H0. In each diagram, you notice some of these asterisks appearing on these figures. They actually correspond to the transition from a boson star to a boson cell in each one of them. In each one of them, these asterisks, they signify, here you find some. So now after this these successful results, we thought of making 3-dimensional plots. And here I would like to define the viewing angle. If you see, I look at the room from one corner, another corner, third place, fourth place, the room would look different. So one has to define the viewing angles, theta, phi. So theta denotes the angle of rotation about the OX axis in the anti-clockwise direction, and it can take values between 0 and pi. Phi is the angle of rotation along the OZ prime axis, which is the new axis obtained after rotation, first rotation. And it can take values between 0 to 2 pi. So now, so this is a three-dimensional plot of metric function A at the center of the star, vector field at the center of the star, a scalar field at the center of. And but the viewing angle here is 60-170. Now I will show you a few more that they each one corresponds to a different viewing angle, 60, 240, and so on. So the same three phase space variables, but a few figures showing the view with different viewing angles. Now we drop A0 and we make plot of B0, H0, and the radius of the boson star, and again obtain those three-dimensional phase diagrams of the theory. Some of them are more clearly visible than others, and so just the viewing angles change. This is just the distribution of the field. So we know that the matter field H is for the boson star would lie within a certain domain. So boson star from 0 up to the radius of the star. And the other three fields are either electromagnetic field or gravitational fields. They are long range forces, so they continue. In this, the inner radius of the boson cell, it has just started the formation of boson cell. In this, the boson cell, these correspond purely to boson cells. Ri is greater than 0. And of course, when lambda is positive, they correspond to the de Sitter space. And when lambda is negative, so the next two figures I show for the anti-de Sitter space. The same distribution of fields. Now, after that, I go to the next model. This is this corresponds to here the scalar field is massless. So only conical potential is there, and there is also no cosmological term here. So you now, but the scalings here, now parameters are different. So the rescaling definitions would be different. We again follow the same procedure. We construct dimensionless constant parameters and dimensionless fields, then also make the arguments of the fields to be dimensionless. And then we study, so we end up with these four equations of motion, which are converted from covariant form to this component form. And again, the U1 invariance of the theory would lead to the Noether conserved Noether current and current density, so charge density and the global charge and the mass parameter M. So in these two models, this is local symmetry. And now we, after doing some of these things, we found that our first four bifurcation points were very, very impressive. They seem to be correct up to 8 digits. So we made this conjecture, if there is a regularity in the occurrence of the bifurcation points, we found it tempting to discover, could there be a whole sequence of bifurcation points, maybe waiting to be discovered, which might display a self-similarity. So we made this conjecture. So here this A, F, and B are constants. And then, so we used the first three bifurcation points and made a prediction for the fourth. And Sanjeev's program gives the fourth one exactly located at this point. So going up to fourth bifurcation point already is very, very challenging, because one has to go up to 8th digit of numerical accuracy. But this conjecture seems to work perfectly well. It seems to be tested here. Now here, these are the phase diagrams of this second theory, second model. Here there is no cosmological constant. However, there is this constant parameter A. So we study this set of bifurcation points with respect to the variation of A. So you can clearly see the first bifurcation point, second bifurcation point, third bifurcation point, and so on. And this part of the diagram is blown up here, zoomed here. So you can see B3. And here it's further, this particular little domain is further zoomed to give you the fourth bifurcation point here. So it's very fascinating and very interesting. In fact, American Physical Society praised our work in their two different articles where they praised our work on this bifurcation points. Then this is a two-dimensional plot of A0 versus B0. This is A0 versus H0. Then these are three-dimensional plots. The logic is as before. The viewing angle is 60 and 100 between A0, H0, and B0. So with different viewing angles, we see a few of these plots. Let me go slowly. So, and then, then we change the A0 by the R0. If it were possible, one could practically, if it were practically possible, one could, because we have a whole set of this value of R0, A0, H0, V0, and so on. One could plot all of them, but we go only up to 3 dimensions. So here it's the radius of the boson star and matter fields at the center of the boson stars. So then with this different viewing angles, you find this. After that, I would come to the, no, is this, yes. So I then finally come to the third model. I have so far presented 2 models, one with massless scalar field without cosmological constant, and the first one was massive scalar field in the presence of cosmological constant. Now here we try a different thing. So this is just a new series of our papers in this direction. And in fact, this is the first paper with non-minimal coupling. So this gives you square root of minus GD4x, gives you the minimal coupling. However, if you include some such term where there is a direct product of the Ricci scalar with phi star and phi. So this parameter xi couples this R and phi star phi. This corresponds to non-minimal coupling. This paper has actually just appeared last month in Classical and Quantum Gravity. So variational principle gives you these 3 equations of motion, and you again construct dimensionless constant parameter, which is only one alpha, and dimensionless field variable h. There is no vector field here. There is no U1 gauge field here. So only h and alpha. Then you again make the argument of this field to be dimensionless, which is r hat. So this is the dimensionless field variable with dimensionless arguments. So actually, these are the equations of motion that you eventually obtain through the variational principle and writing them down. So this is these are for the metric functions, and this is for the scalar field, matter field equation. And these are, so this you obtain from the Einstein equations, these 2, and the last one. So you see that equations are little more involved because of the presence of that non-minimal coupling term in the theory. So that is the point. You again choose the appropriate boundary conditions. Here, the U1 symmetry of the theory would be a U1 phase symmetry. So because it's a global symmetry and not a local symmetry, as it happened in the first 2 cases. So you again obtain the charge, global charge of the boson star and the mass parameter m of the boson star. With that, then I just present a few results. So in this figure, we plot matter field at the center of the boson star versus the parameter alpha, and this for different values of xi, which couples, which gives you the corresponds to the non-minimal coupling term. So you see, when you increase xi, what happens? This term, this plot comes down here. This black one corresponds to xi equal to 1. This one, and this corresponds to xi equal to, so non-minimal gravity, and this is minimally coupled gravity. So as alpha increases, H0 initially decreases like this, and after some limiting value of alpha, it starts monotonically rising and finally ending up into the damping. So
Professor Kulshresht, you have 3 minutes.
okay, thank you, Sanjay, thank you. So the second one is the plot of the radius of the boson star with alpha for different values of xi. And here you see, initially when we increase alpha, the radius of the boson star decreases, and after this value, it again starts increasing, and then eventually ending up showing you the oscillating pattern, which actually corresponds to the oscillating pattern of the matter field at the center of the star. So this is the spiraling pattern of the radius R0, which is blown up here in this figure. And if you plot mass versus alpha for different values of chi, the results are so transparent that you see increasing chi implies that the coupling of a scalar field with gravity increases and increases. So this allows to sustain higher masses and enable the formation of more massive and more compact boson stars. So this is the thing which is very clearly visible here. And the charge parameter, the global charge of the boson star, also follows the same pattern as that of the mass. So a spiraling effect here after this value limiting alpha, and prior to that, it increases along with the increase in alpha. So this is mass with respect to radius. So when you reduce the radius, the mass increases. You see, when you reduce the radius this way, the mass increases, or other way around. So, and the same applies also the charge of the boson star. This is the last figure, which shows the mass versus the charge. Yuta very much loves these figures. And here you see that M increases linearly, almost linearly, up to this limiting value of alpha. And then it starts making, it's not so visible here, but then you get these spirals here. So after this alpha, this value alpha going to alpha max, a spiraling behavior is observed, and this is becomes more massive as we increase chi for a fixed value of alpha. So with this, I think I'm through with the all my results. At the end, I would just present the a quote from Mr. Pythagoras, who said, "Stars in the heavens sing a music if we only had ears to hear." With that, I would end my talk. And thank you once again, Sanjay. Thank you, Alok, very much.
Thank you, Professor Kulshesh. The talk is open for questions. We can have one brief question in view of the time.
Okay, welcome.
I see Professor Haridas.
Yes.
Your hand. Okay, that is not a raised hand. Is it a raised hand or is it a clapping hand? Okay, that's a clapping hand, not a raised hand. Okay, so I'm just looking for raised hands, and at this point, I do not see one. So, Professor Kulshesh, thank you very much. For this talk. Gargi, did you want to say something? Gargi, you're muted.
Okay. Okay. So,
Okay, fine. So I think that in view of the time, we will proceed further with our next speaker, Professor Patrick Dasgupta.
okay, Sanjay, thank you very much. I mute myself.
Thank you. Thank you. Professor Patrick Dasgupta is a long-time friend and colleague at Delhi University. And his topic is quantum Shardula measurement problem and gravitational wave detection. Professor Alok Mishra mentioned that Patrick is not quite well, and he has sent a video, which Professor Mishra, please show it to us. Is that Patrick visible? I can see Patrick. I can see a photo of Patrick.
Right. So that's a video that I just shared. So may I start the video?
Yes, please do.
Okay. Thank you so much. Thank you.
Good afternoon, everyone. First of all, I am very thankful to the organizers for enabling me to pay tribute to Professor late Mitra. And today, the topic I've chosen, namely the foundations of quantum theory, is because in the decade 2000 to 2010, Professor Mitra had become greatly interested in the foundational aspects of quantum theory. In fact, I still remember when Professor Roger Penrose was visiting Delhi, there was a meeting organized in the India International Center, and there Professor A.N. Mitra talked at length about the foundational aspects of quantum theory. Now, we all know that this meeting was very important because, one had to pay the tribute to one of the outstanding theoretical physicists of India, namely Professor A.N. Mitra. And I'm really thankful to the organizers like Alok, Gargi, Professor Haridas, and many others, and in particular to Alok, who had taken a great deal of efforts to make this meeting a great success. Now, let me begin my talk. Shardula in the ancient Indian context is essentially superposition of several distinct animals, and they are found in paintings and as well as sculptures like this one, where you can see the head of an elephant superposed with the body of a lion, and such Shardula figures are very common in many of the sculptures of South Indian temples. And we all know that in quantum theory, one indeed talks about superposition. For example, in the celebrated Schrodinger cat problem, we know that there is a whole entangled system of counters, the cobalt-60 nucleus, as well as living systems like cat. In effect, you have an entangled state where one of the states, which is in the product state, is the cat dead state entangled with another cat alive state. And that is the reason I talked about Shardula. And one of the celebrated problems, an outstanding problem indeed in quantum theory, is that when we observe, the state collapses. So either we see the cat dead or cat alive in such a configuration. The question is, what leads to this collapse? We know that when you have a quantum system which is evolving on its own without any intervention from any measurement apparatus, the state evolves according to the Schrodinger equation, IH bar d by dt acting on the state is equal to the Hamiltonian operator acting on the state, and this evolution is completely deterministic. However, the fourth postulate of standard quantum mechanics says that if I want to measure the observable A, the eigenvalues are An and eigenstates are Un corresponding to eigenvalues An, and when we observe the quantum system using a measuring apparatus, then in general, the probability that we observe one of the eigenvalues An, that probability is given by the Bond rule, namely the mod square of the inner product between the eigenstate Un and the quantum state. However, we all know that a measurement is nothing but an interaction between apparatus and the system. Apparatus is also quantum mechanical, and therefore the interaction should be described by an interaction Hamiltonian, and the apparatus plus system should evolve according to the Schrodinger equation, where the Hamiltonian is nothing but the Hamiltonian for the apparatus, plus the Hamiltonian for the system, plus the interaction Hamiltonian. And the whole system must evolve in a deterministic manner. But why should we get the probabilities which are indeed what is seen whenever there is an observation? Where does the probability come from? One of the key things to sort of highlight is that whenever you use the usual unitary evolution, one sees the entanglement between the states of the system and the apparatus. And you have different branches in which the pointer state and the quantum state, they are entangled with each other, and different branches corresponding to the different eigenstate of the system, the branches don't talk to each other. The other key factor is that during the interaction between the apparatus and the quantum system, at the detection level, one finds, and this is something very general, that the few degrees of freedom of the quantum system interacts with innumerable degrees of freedom of the apparatus. And of course, this is the origin of the increase in the entropy, because unless you keep track, you don't know which are the degrees of freedom of the apparatus of the pointer state which has got influenced by the interaction when there is a collapse. Now, in this talk, I will share some of my thoughts regarding what could be happening and could these ideas at some point of time explain the origin of the probabilities. The first thing is, let's ask a question. After all, gravity is universal, and when one takes into account the quantum theory of gravity, we know that there are the Planck numbers, Planck mass, Planck length, Planck time. They give us some limitations to the ideas of classical general theory of relativity. Here one can ask, is there a Planck number of degrees of freedom? Because here we see that a large number of degrees of freedom are involved in the apparatus that gets entangled with the quantum system. So if one takes the Planck mass, which is about 10⁻⁵ gram, and divide by the electron's mass, then one gets the number 10⁻22, which is very close to the Avogadro number, which is a hallmark of macroscopic systems. And of course, the reason I've chosen the electron mass is because most of the detectors in the apparatus, they essentially contains of atoms which has electrons and protons. If one chooses proton, the number will come down to about 10⁻90. Now, the idea that I would like to sort of stress on is that we know that there is, from quantum theory, there is a number phase uncertainty. Now, could it be that when the detector degrees of freedom exceeds the so-called Planck number, some kind of fluctuation in the phase, the random fluctuation in the phase, could it be the origin of the probabilities? Now, here one should also stress on the fact that when the quantum system is interacting with the apparatus, the measurement timescales are very short, and therefore the amount of energy exchange between the quantum system and the macroscopic apparatus, that energy will be uncertain, which will be given by the energy time uncertainty. And such fluctuation in the energy of exchange, according to general relativity, would cause metric fluctuations. And metric fluctuations will lead to fluctuation in the proper time. After all, the evolution of the state, one would think that it's the proper time which should be more relevant than the laboratory time. And fluctuation in the proper time can cause phase fluctuation. So the number, the Planck number, and the relevant phase fluctuation resulting in such random number, could it be the origin of the probabilities? To highlight a typical measurement scheme, namely the spin measurement using a Stern-Gallic apparatus, we know that the real measurement takes place when the entangled state wave function telling the trajectory of the electron going towards the top part entangled with the spin down state, and trajectory telling us the apparatus, the electron's spatial wave function evolving towards the bottom part, direct product up state. The final measurement takes place when the electron interacts with some detector system like a photographic plate, etc. And there, after the interaction with the detector state get deep, so which is composed of innumerable number of atoms, different atoms get excited. And these atomic excitation, there is, because of uncertainty in the energy, there'll be uncertainty in the phase, there'll be fluctuation in the phase that can lead to random phases. And could it be the origin of the probabilities? And this can be generalized to any arbitrary quantum measurement using the kind of interaction Hamiltonian, which is a product of the quantum variables and the operator. Supposing one wants to measure the position of the quantum system, then one can have a interaction Hamiltonian that couples the position operator of the quantum system with the pointer momentum states, and one can easily show that such an interaction Hamiltonian would be useful in reading out the position, but the final state is still an entangled state, telling us that when the pointer position is
Hari, what's the problem?
the quantum position
Hari,
is x1, and so on.
are you
And
listening
by
me?
reading the pointer variable, one knows
Professor
which
Haridas.
electron, but still the whole system is entangled. When does it? How does the mod C1 square, mod C2 square, etc., as probabilities arise? So one of the things is, as I'm highlighting, that probably the unitary evolution should be recast, that this T must be replaced, not the laboratory time must be replaced. The individual branch should evolve according to the corresponding proper time. And whether that could lead to the so-called Born probability. Of course, the gravity-induced collapse have been talked about by Diossi, Penrose, Ciano, and many others. And there are other many worlds interpretations, etc. But the main problem is in the many world interpretation, the branches, different branches, they don't talk to each other because they are happening in the Hilbert space. And the many world interpretation also doesn't, unless you use decoherence and averaging over the environmental states, then one doesn't get the Born rule, namely the mod square of the individual coefficients in the linear expansion. So in the many world interpretation, yes, all the branches occur, but the branches don't talk to each other. Is there a way we can make the each of the branches in the many world talk to each other through this random phase so that one gets the Born rule? Of course, I mean, the solution to the problem requires much harder work. The question is, can we sort of think as to what could make different branches talk to each other? I'll skip some of the slides. Let me try to highlight by using a thought experiment, trying to exaggerate the role of gravitation here by taking the final detector to be fairly, 1 milligram masses. So imagine that our detector is nothing but 2 blocks, 1 milligram weight reflectors, which is essentially in an unstable position. So we have 2 such unstable equilibrium 1 milligram reflectors. And let's say one has a photon, a single photon state interacting with a half silvered mirror, so that the state now is a superposition between 2 states, 2 orthogonal states. That is, the state is Cn1 plus C2N2 after interacting with the half silvered mirror. And according to quantum mechanics, after the interaction, we have the state Cn1, N2, psi1 becoming psi1 star, namely the 1 milligram falls off after being hit by the photon, plus C2N2 and psi2 changing to psi2 star after being hitting. And it will be an entangled state. But the key thing to realize is gravity is universal. Gravity cannot be screened. The whole problem when this psi1 is in transit to becoming psi1 star, there is the gravitational potential is changing, and due to that, proper time is changing here, and this proper time changing, the fluctuation, gravitational fluctuation will also affect the other bob. Similarly, this bob in the other branch changing to psi star, falling, its gravitational potential will also affect psi2 star, psi1 into psi1 star. So in reality, the time evolution will develop the following kind of a system. It will be C1 N1 prime, namely after hitting the state of this branch of the photon will change, psi1 star, and the time involved, the time will depend upon not only psi1 star but also psi2 star. And this whole branch, as you can see, that the psi1 star depends upon psi2 star and psi2 star depends upon psi1 star, and the time itself depends upon both the branch. So in other words, what we see is that if we really take into account the proper time into consideration, then the 2 branches are actually talking to each other. And because gravity cannot be screened, and no matter what kind of detector you use, whether it's a photographic plate, the particles in the top branch, they share the energy, and there's a lot of fluctuation here. The gravitational fluctuation will also influence, however tiny it is, will also influence the particles, the detecting atoms in the other region, because in no way gravity can be screened. And therefore, this cross-talking would essentially bring about a nonlinear evolution. And perhaps, and we know that there are ways, if you modify the Schrodinger equation by using certain nonlinear terms, you can indeed get the Bond rule. For example, the Gregorian-Coase paper in 1995. So indeed, the gravity can bring about a nonlinear problem. Since the time is limited, I will skip some of the slides. I will come to the end part, namely the fact that the metric is the GR metric should also be described in quantum mechanical way. The question is that can we test whether the GR metric is indeed quantum mechanical? Here, a host of authors, starting from Amelino Camellia in 1999 to Dyson, the 13 and recent work of Parekh, Wilczek, and Zaharadia, they have all talked about if one takes the quantum state of the gravitational wave, how does the geodesic deviation, namely the separation between two freely falling particles, gets affected? And after all, the LIGO detectors are nothing but the two mirrors, are nothing but freely falling test particles. And these work shows that in principle, the geodesic deviation will have random fluctuation, and such a thing would appear as a noise in the LIGO detector. And depending upon, of course, the quantum state of the gravitational wave, impinging gravitational wave, the noise will have different form. And in principle, therefore, LIGO detectors can be used to check whether gravitational wave indeed they are in reality quantum states, because there are a minority view that perhaps the geometry and metric, they should not be quantized. There's a lack of time. I must stop here. It's unfortunate that because of certain limitations that I'm out of India and I've been traveling and I have serious limitation with internet, I'll stop here. And if there are questions, they can be sent by email to me. Thank you for your patience. And this is a picture from the paper by Parekh, Wilczek, and Zaharadia, where they have computed what kind of fluctuations arise between two freely falling particles when a quantum gravitational wave impinges. Thank you very much.
Okay. Professor Alok Mishra, I guess since Professor Patrick Dasgupta is not in our is unable to join the meeting, we will not have a direct question answer session with him, but as he has said, questions can be emailed to him.
Absolutely.
So we can then move on to our fourth speaker, Professor J.D. Anand, who is one of my former teachers at Delhi University and a former colleague of Professor A.N. Mitra. I'm very happy to welcome you to give your talk here. Please share your screen.
Thank you, Professor Jain. Hello.
Yes, we can hear you and see your screen.
Yes. Okay. Is it okay?
Yes, please. Yes, you can start. We are able to see things, and
I'm grateful to the organizers for inviting me to this talk, and I had a long association with Professor Mitra since 1960, when he joined the department as reader. I was then pursuing my PhD thesis under Professor Majumdar, and Professor Mitra took a lot of interest in students of Professor Majumdar also. So in the early 60s, there was a lot of interest in Reggie poles, dispersion relations, resonances, and particle physics. So at that time, Professor Mitra was pursuing the separable potentials. So he suggested that why don't we apply separable potentials in the complex angular momentum plane. And that originated for writing a paper on separable potential in the complex L plane, which we published in Physical Review 63. After that, I had another paper with Professor Mitra on PP scattering and Reggie's interaction, which we published in 65. So these two papers became the part of my PhD thesis in 65. So Professor Mitra took a lot of interest in my development. He recommended me as a UNESCO fellow to visit USSR in 65 and 66. And he also recommended, when he was the head of the department in 74, he promoted me from permanent research associate to permanent lecturer in 74. So I had a lot of personal contact with Professor Mitra. He attended my marriage also in 1966. So he was he helped me in promoting multiple theoretical physics areas. So I owe him everything which I have developed. So actually, I have to choose a topic because now I am 25 years behind this research, and I have chosen a topic which we had collaborated with my colleagues on various aspects of neutron stars. We had actually uh, studied mass radius relation of neutron star and bulk viscosity and emission of neutrinos and antineutrinos as the process of cooling neutron stars. So I had a collaboration with Professor Ashok Goel, V.K. Gupta, and Santokh Singh. So we had a number of students also. So a lot of people may be knowing now what are neutron stars. So neutron stars are formed because neutron stars are formed from the remnant core of the massive collapsed supergiant star. And this neutron stars is the densiest object in the universe, second only to black holes. And typical properties of these are mass is about 1.4 or so, radius is about 10 kilometers. And it is composed of mostly neutrons. So protons and electrons, they fuse under pressure to again have additional neutrons. So since at this temperature, neutron has a high temperature also, and this at the time of formation, when it is collapsing, what happens is that the rotation, its rotation is increasing due to the conservation of angular momentum. So this neutron star is actually supposed to be stable due to the neutron degeneracy pressure, like the degeneracy pressure of electrons in the white stars. So in the case of neutron stars, previously, Jana, it was found that the neutrinos and antineutrinos as produced from the neutrons are not sufficient. But with the latest detection of neutrinos and antineutrinos, this reaction N going to P plus E plus neutrino, antineutrino, and N plus P plus E is going to N plus new electron. So these processes become important. And if the energy of the electron is very high, then muon couple pairs also take part. So I have just given one fastest known PSR. So this is about the neutron stars, because a lot of people know neutron star very well. So I will actually, I have chosen a topic of radial pulsations of neutron star, and this was published by me and along with my friends. So I would like to report this thing in this colloquium. So in studying the radial oscillations of neutron star, it is important to have a equation of state is equation of state is very central to this, because if we know the equation of state well, we can do a lot of things. Now, it is very, we don't have an equation of state for all the energies. So there are actually a lot of cases for the high energy as well as low energy equation of states. So the famous equation of state and at the same time, we also know that in the case of neutron star, there is a strong magnetic field at the surface as well as interior. So at the surface, the magnetic fields are of the order of 10 to the power 13. And interior also, the magnetic fields are quite high. And these neutron stars are known as magnetrons. So we also wanted to study radial oscillations in the presence of strong magnetic field. So for equation of state, we have chosen the low energy in the equation of state from Baum, Patrick, and Sanderson model. And in this model, the pressure of the hadron matter below the neutron drip is given by this thing. And this electron pressure is also given. The lepton pressure as well as energy is given. The number of electron is given. And along with the right-hand side, I have given a table where for the medical purposes, the table is useful. So the matter consists of, if I consider an atom having A and Z, and we can write down the energy, and at the same time, we can find out the energy as well as pressure from this thing. So for high energy, we have chosen the relativistic mean field theory as given by the Ellis, given by Ellis. And we have incorporated the magnetic field modification due to the particle momenta and density. Actually, the pressure is given like this thing. The first part is the pressure due to N, P, and E. And we have also taken omega as well as rho mesons. We have also taken the scalar sigma particle. So we have written down the pressure and energy, and the potential of the sigma is given. So these neutron, proton, pressure and energies we have given in details on the right-hand side. So when we want to find the pressure and energy, and they depend upon the magnetic field, they depend upon the. So what we have done is that we can choose a nuclear density, and from that thing we can find the parameters of the pressure and this thing, and then evaluate the pressure and energy, which we will be using in the Tolman open number equations. So here the chemical potential, because we have actually taken the neutron as a degenerate free particle, and the chemical potential of the neutron is given by proton and electron. So for radial oscillations, we have taken a small perturbations, and they are governed by the general relativistic equations, which actually Professor Kulshist has talked about. So the Tolman open-number-Volkoff equation is written on the right-hand side, and it involves the pressure gradient, mass gradient, and the nu. We have chosen the ds square as this thing. So the here delta r by r are new variables which we have chosen. So for given density, because for given energy density, pressure and energy are obtained from the equation of states and used to calculate mass and radius from these equations. And because we have chosen the time dependence of the harmonic oscillation as e raised by I sigma t, and we have written down the equations governing radial adiabatic oscillations as 41. And this is the famous Stern-Liouville eigenvalue problem. And from the properties of this equation, we can see, and the variables f, g, and h are given on the right-hand side, along with lambda and the adiabatic index. So the boundary conditions to solve the equations are that zeta at r equals 0 is 0, and the pressure change in pressure at capital R is 0. With these boundary conditions, we solve these equations, and it is an eigenvalue problem, and it is from the properties of this famous eigenvalue equation, it is clear that sigma square is real, and the fundamental mode is greater than other things. So sigma 0 is greater than sigma 1, sigma 2, and so on. So by combining equation of state both at low and high energies, I have just, we can find out the model of the neutron star. And here the magnetic field we have chosen as 0, 1 in 10 power 3, 5 in 10 power 3, 1 in 10 power 5, MeV square, where 1 MeV square is 1.69 into 10 power 14 G. And the various coupling constants are given on the right-hand side, which we have chosen from Alice. So we solve the Tolman-Volkoff equations for mass radius relation, gravitational shift, and density profiles, adiabatic gamma. So by solving these equations, we find the fundamental and excited these frequencies. So the results are that mass radius relationship with magnetized neutron stars support higher masses and strong fields, more compact configurations. So we have plotted for A, B, C, D on the right-hand side. So mass redshift relationship is also plotted, and redshift increases with mass and magnetic energy. Can be an observable indicator of field strength. And for in the third figure, we have given the this thing pulsation periods, stability and pulsation periods we have given for typical neutron star of 1.4 mass, solar mass. And magnetic field has the minimum effect on radial stability, and pulsation frequencies are not significantly altered in this mass range. We have done this thing for first excited mode also. So we conclude that magnetic fields affect minimum mass and compactness, but not affect the stability of the typical neutron star. Helps define models for magnetrons and related astrophysical events. Sets groundwork for future studies involving gravitational wave emission and magnetic fields. And we have also incorporated the temperature effect in the other papers. So I will give the references for our completeness. And thanks, Sanjay Jain. Thanks, Professor.
Thank you, Professor Anand, for the talk. The session is open for questions. I can see a thumbs up sign from Professor Utah in the participants list. However, yes, Professor Utah, your hand is raised. Please.
Yes. Thank
Please.
you very much for this nice talk. My question concerning your main result, that the magnetic field strength does not affect so much the stability. Do you think this is a rather general result, independent more or less of the different types of equations of state that one can use?
There you go. Professor Jan, can you elaborate the question, because I'm very happy.
Yes, I think the question is one about the generality of the result. Maybe Professor Utah, you can repeat the question. I think.
Yes, sorry if I wasn't clear. You have this nice result that the modes are basically not affected by the strength of the magnetic field. And my question is this more or less independent of the equations of state that are being used? What is your opinion on that?
Actually, there are because I retired in 2000 and before 25 years before, and this work is done in 1998 and so on. So at that time, it was quite interesting, and it was found that these nuclear mean energy, this equation of states were quite helpful at that time to understand, because I had also worked in the strange quark stars, where we had taken UDS quarks, and there also we found the mass radius is compatible up to 10 kilometers and 1 solar mass. So that is why we have chosen these nuclear equations as models.
Yeah, I mean, these are quite attractive.
Yes, I think it would be interesting to address that question and see to what extent this independence holds, right? Okay, thank you, Professor Jaydevanand. I don't see any further questions. So thank you very much for your talk and your comments about Professor Mitra. And we will go on now to the next speaker, Professor Naresh Dadhich, whom we missed this morning, but it's very nice that he is able to join us. Professor Dadhich, could you please share your screen and start your talk? He's going to talk about geometry-driven dynamics of the fundamental forces. Professor Dadhich, can you
right.
you unmute? Yes.
Now,
very good. We can hear you.
Now let me share the screen. This is the one. Oh, sorry. This is the one. Do you see the screen?
Not yet.
Well, okay. Should I say again, share the screen, or what do I do? I see the screen. It's here. Here.
Yes, it's starting, I think.
My talk is here. Does it come?
Okay, we don't see your screen yet. We don't see the talk yet. We are seeing a post attendee, a Zoom post attendee screen.
Now, so can somebody tell me what to do? I don't know. Yeah.
Professor Alok Mitra, maybe.
So share screen. Yeah.
Professor Dadich, I think if you rejoin it again, because it's post attendee, then I would prefer to join once again, then maybe it would be visible.
But we can see him. We can see Professor Naresh Dadich we can see him, but his screen is, you might be sharing the wrong screen. Yes, it's right. Now we got it. Yeah, it's come.
Oh, it's come. Okay,
yes.
Good.
Yes.
Good. This comes right. Okay. Right.
Yes.
All right. So thank you. So let me begin with the.
Sorry, Professor Dadich. Sorry, is Alok here? Is it possible for you to go full screen by pressing Control L together?
Just a minute. Let me see. Full screen somewhere, I say.
What do you want me to do?
I want to get that thing right. Well, you people are blocking the thing here. Your pictures on the right. Right.
Okay. That is not affecting us. That is just the view that you have chosen for your Zoom meeting, Professor Dadich. But I think that we can see the screen.
Is this okay?
We can see it clearly. It's not fully, the full screen is not visible in the sense that the bottom of the screen, you will have to scroll up. I think it's a PDF file, so you can scroll up and.
Yeah. Now it is coming, right? I just scroll down.
Yes, the plan is plan of the talk is visible.
Right. Okay.
Professor Alok Mishra, is this all right?
Yeah, sure. Yeah, please go ahead. Sorry. Yeah.
So let me begin by thanking particularly Alok Mishra for asking me to give a talk in this very important meeting celebrating the life and work of one of the most distinguished physicists, Professor Mitra. Which I was not his student, but yes, in the later years, we did meet, and it was very interesting that he will always ask some conceptual issues. And so I'm with a very fond memories. I dedicate this talk to Professor Mitra. Let's begin with. The idea here was that how do we distinguish a fundamental force from the other thing? And the question I said is that its dynamics should not be prescribed, but should follow from some general principle. So that's the plan of the talk, to say that the fundamental force dynamics should follow from some general principle of conservation of something or the geometry. So for example, the Newton's and Coulomb's laws are driven by the conservation of flux. That's how you get the inverse square law. Now let's come to begin with that in the absence of force, what should be the state of space and time? So we want to first start with the characterize the space-time when in the absence of all forces. And in doing this, the two constants of space-time structure will emerge. And they emerge without any reference to any dynamics or any force. And the fundamental forces then will emerge when the space-time becomes inhomogeneous. So homogeneous space-time is free of all forces. When it becomes inhomogeneous, then the fundamental forces emerge. And of course, which space-time will depend on what sort of, what kind of force we are referring to. So let us begin from the beginning. When we say space is homogeneous, we can freely exchange x and y. And the free space-time is homogeneous and isotropic. But also the free space-time does not distinguish between space and time. So time is also homogeneous. So whatever I do to x and y, I should be able to do the same thing for x and t. But then you pounce upon me to say that no, their dimensions don't match. So you have to bring the things on the same dimension. So then my question is, yes, this is the general principle, homogeneity, which has to be respected. So if the dimensions don't match, make them match. And for that, to make the dimension match, we need a universal velocity. To bring t and x on the same footing, and this is how emerges the first constant of space-time structure, the universal velocity c. So what does the c does? It binds space and time together into space-time. So now we go from the three space in the three space to one time to we go to a four-dimensional space-time. So we have a one paradigm shift that we live in a four-dimensional space-time, not really in a three space and time. So free space-time. So in absence of this, the free space-time should be homogeneous, which would mean the space is homogeneous and isotropic, and time is homogeneous. The next question is, what should be its geometry? A natural answer is, a geometry must be also homogeneous. Now, geometry is defined by the Riemann curvature. So Riemann curvature must be homogeneous, means Riemann curvature must be covariantly constant. And hence, I should be able to write Riemann curvature in something which is constant relative to the covariant derivative. And that is, of course, the metric. So you write the Riemann curvature, some constant lambda to give the dimension of 1 over length square, and the combination of the metric metric coefficients respecting the symmetry of the Riemann curvature. So we have naturally come to the homogeneous space-time, which is free of all forces, is a space-time of constant curvature, not necessarily of zero curvature. And that constant curvature is what is that we denote by lambda, which could be positive, negative, or zero. And what it should be, that it should be left for the experiments and observation to determine. So at the moment, so the free space-time has this homogeneous geometry of constant curvature. So lambda thus emerges the second constant of space-time structure on the same footing as the universal velocity c. And these are two the most fundamental constants we have, because no other constant yet has been synthesized in the space-time structure. Having said that, now let's go further. What happens when space-time becomes inhomogeneous? Again, a very simple thing, right from the classical mechanics, we know that inhomogeneity signals the presence of a force. So now the question is, what should determine its dynamics? And the answer to that is that I have only the space-time and its curvature. There's nothing else at our disposal, so it has to, the dynamics of this force arising out of the inhomogeneity of space-time should also arise from the space-time curvature itself. So now we ask the question, is there anything we know for as a property of the Riemann curvature? In differential geometry, there is a very celebrated identity called the Bianchi identity, saying that d square equal to 0. The properly defined derivative twice d square is identically 0, which the John Wheeler famously had termed in a poetic way that boundary of boundary is 0. And that is what is the geometric way of expression of conservation law. Now, well-known examples of this d square equal to 0, we all know, but we never recognize them as a differential geometric statements. Curl of a gradient is 0. The divergence of a curl is 0. So you have a scalar field, you have taken care of the vector field. Now you say that if you go to the higher order, you have a tensor field. Then the analog of the next order thing, the cousin of this is that Bianchi anti-symmetrized derivative of the Riemann tensor must 0. This is what is called the Bianchi identity. So we have a Riemann curvature, its anti-symmetrized derivatives is identically 0. So this is given by differential geometry. We have nothing which is, we don't have anything from outside. Now, any tensor equation you have or any tensor relation you have, simplest thing you can do is to contract it, take its trace. And ask first the question is, find a trace of contraction which is non-vacuous. And this is the only what you have written here is the non-vacuous trace of the Bianchi identity. So you're contracting this, and what does it give us? This gives us a second-rank symmetric tensor GAB with vanishing divergence. And this GAB is given in terms of the Ricci and the Ricci scalar. I think the scalar has gone out this thing. And the Ricci is the first contraction of Riemann. So as a matter of fact, what we obtained, everything started from the Riemann. So we obtained a second-rank symmetric tensor, which is essentially a creature of a Riemann tensor. So we have this, we come up to this, right? Now we say that if a force is universal, by which we mean that the force which links to everything that physically exists, and which means hence it has to be present everywhere. It should therefore be described by some universal entity which is present everywhere and which is shared equally by all that exists there. So that can't be anything other than the space-time itself. And the force should be described by then the inhomogeneity of this space-time, and that is when the Riemann curvature is inhomogeneous. So the force could, another way of looking at it, should arise from the geometry of the space-time through the Riemann curvature. The dynamics that follows would be the dynamics of that universal force. So now let's get back to this. So what we were? We obtained a divergence-free second-rank tensor, which is GAB. Now in a simple farmer's way of integrating, let us integrate this equation. So what the simplest way to do is to say, okay, write this GAB, add a constant of integration relative to covariant derivative, that is your lambda GAB, and write another proportional to a tensor TAB, demanding that it is symmetric and its divergence is 0. So this is a formal way of doing this. Now we know on the left-hand side is a creature of Riemann tensor. And the Riemann tensor is involves the second derivative of the metric and square of the first derivative. So on the left-hand side, I have a second order differential operator analog of del square phi. Then you would say that on the right-hand side, if I could identify a source, then it becomes an equation of motion for this force. So the thing here, the new thing which I have, lambda is GAB is a constant of integration, so that's nothing. Is a TAB. Now the TAB is the source which makes space-time inhomogeneous for all particles, which means the TAB should be a measure of some property which is universally shared by all that physically exists. And that property then is uniquely the energy momentum. So if I identify TAB with energy momentum, then the equation 5 above is the equation of motion of Einstein gravity. So in a very simple way, we derive the equation of motion for Einstein gravity from when space-time becomes inhomogeneous. So here the question which I wanted to say, sorry, so that the universal force of gravity, its dynamics is determined by the geometry of the Riemannian space-time and its curvature, without adding anything broad, no prescription of any kind from anywhere. So that's my main main message from this talk. So what we say. Now you see that maximally symmetric homogeneous spacetime, which is free of all forces, is of constant curvature, not necessarily of zero curvature. When that curvature is inhomogeneous, when force is present, then curvature becomes inhomogeneous. In contrast, our textbook view is no gravity means Riemann curvature is zero. Now, which is in our language saying the lambda is zero, which you have put it by hand. You demand this. But actually, it should be left to the experiment to say whether lambda is zero or non-zero. In this picture, paradoxically, you have maximally symmetric space-time, homogeneous space-time of constant curvature, which has non-zero curvature, and the space-time is homogeneous, but curvature is non-zero. Hence, but it has still, so that constant curvature will give you a non-trivial dynamics. As a matter of fact, maximal symmetric homogeneous space-time should have no dynamics. It should be a free of thing. In a new perspective, in our way of looking at it is, no force, absence of gravity means space-time is homogeneous. Presence of force, space-time is inhomogeneous. As it is in the classical mechanics, you go from homogeneous to non-inhomogeneous, you come from that zero force to the force. So there is smooth transition from homogeneous to inhomogeneous as force appears. C and lambda are two constants of free homogeneous space-time. They are the most fundamental constants that I have. Now there is another one ticklish question we have to address is of the vacuum energy. Now vacuum energy is created by the fluctuations produced in the vacuum produced by the metal fields. And since gravity is universal, all forms of energy must gravitate. So that is true that the vacuum energy which is taken care of should gravitate. And when you try to write a stress tensor for the vacuum energy by all your renormalization, throwing away the infinities, it has the same form as the lambda GM. And that is where lambda gets slated against the Planck length. And then you have this monumental discrepancy of 120 orders of magnitude. So lambda gets beaten by Planck length. But here you should know that lambda comes out as a natural fundamental property of a homogeneous spacetime. But that's right. Now the question here is, so we have this conflict here. Vacuum energy must gravitate. Then the question we should ask is, should it gravitate through a stress tensor? And generally you say that yes, all matter fields gravitate through a stress tensor. Should it gravitate this? And that's the question which we want to ask. So that we can forget about. But we say that gravity is universal, energy, any form must gravitate. So vacuum energy must also gravitate. The question we are asking, should it gravitate through a stress tensor? So the thing which would require is that gravitational energy does not have, vacuum energy does not have an independent existence of its own. it is created by the matter fields that produce the vacuum fluctuations. So it is a secondary source of gravity. And the answer is the secondary source, that should it sit on the right-hand side of the equation along with the mother, the matter field. This other thing we said, that one other question is, have we not done something similar with your taken care? Gravitational field energy or gravitational self-interaction. That is also a secondary source created by matter. And we wrote no stress tensor for that. It was so the gravitational field energy or self-interaction does not interact with a stress tensor, but it interacts by enlarging the framework. So as a matter of fact, this asks for that it cannot be incorporated in the Newtonian theory. We need a new theory, and it is incorporated in the curvature of three space. Now, this we really do not recognize because the space-time itself is curved, and nobody bothers about this. But if you really want to see that in the Schwarzschild solution, how is the self-interaction included, then you will find that it is included in the space curvature. So for example, if you keep the dr square coefficient 1 and write only 1 plus 2, 5 for dt square, it will incorporate the Newtonian gravity, RW dot equal to grade phi. But when you include the dr square coefficient inverse of the JTT, then what happens is the self-interaction gets, the self-interaction term gets worked out, and it has, and the curvature, the effect of the self-interaction goes into curving the space. So this is essentially to saying, coming from the flat three space to curved three space incorporates automatically the self-interaction or the gravitational field energy. So in general, you have the inverse square law remains valid in GR, and your is the space curvature which takes. So now the question is, what the vacuum energy is on the same footing as the gravitational energy. If the gravitational energy does not interact through stress tensor, so must vacuum energy must not. And so we require a enlargement of the framework. Another argument you can say that, you see, this is your force you have for the particle. M into acceleration is the force. Its fluid thing is rho plus P du dt equal to the gradient of pressure. Rho plus P here is the inertial density, which is an analog of mass. For the particle, when mass vanished, we needed a new theory to incorporate its motions. So we needed a special relativity. Similarly, here rho plus P is 0 for the lambda if you take the lambda as the matter field. So you will need a new theory for this. It cannot be incorporated in the existing general relativity. So you need a new theory, and that new theory we will not know unless we have a quantum theory of gravity. So vacuum energy must gravitate like the whole. So the general principle, we say that all the secondary sources must gravitate through enlarging the framework, not through the stress tensor. And I would say, to me, one of the compelling motivation for vacuum for the quantum gravity is to include the gravitational interaction of vacuum energy. Once that is realized, lambda is free of the Planck length. You can otherwise say in this 120 orders magnitude, you can make a more meaningful statement that in Planck area, the inverse measures this much. Okay. So lambda was determined in 1997 in the supernova explosion after 100 years of its introduction. Had Einstein followed this argument, he would have realized, oh, I'm doing badly. Then he probably would have made the greatest prediction of his time that there would be sometime in future, lambda will dominate over the expansion of the universe, and you will have an accelerated accelerated expansion of the universe. No need for the dark energy or the phantom things or anything that kind. Lambda, that's, I think that's okay. Now we say, okay, this all was fine. Now we say, how do we talk about the other fields? So the question we ask is, the next thing is that a force which links to a particular charge. So you have a gauge vector field. Now here you ask, what is the relevant geometry, relevant space-time geometry? And that turns out that the principal tangent bundle of space-time.
Professor Dadish, you have 5 minutes.
I'll in 2 minutes. I will keep it within this.
Okay.
So that its curvature is given by the two forms which satisfy the Bianchi identity, which means that it is derived as a curve. So it's antisymmetric. Since it is antisymmetric, its double divergence is identical 0. And which, like as we integrated the Bianchi identity, you similarly integrate this, gives you the divergence of F as the for current, conserved current. And that's what gives you the Maxwell field. And so you get the, now the Maxwell field, so you have a vector field. So when there you can now attach some other symmetries. So when you have a U1 symmetry, then it is your abelian gauge field you get. But now you say, okay, that is from SU1, abelian. Now you can get a non-abelian. You can have SU2 and SU3, your Young-Mills field. Everything goes same way, except that now you will, your derivative, you have to define the gauge invariant covariant derivative. The rest of the thing what we did for the Maxwell field goes through the same argument. And again, you will have the dynamics of these fields coming from the Bianchi identity of the tangent bundle space. So that's that. So the question is, the dynamics is given by the geometry of the relevant space-time. And lastly, a minute to go, I can say we have 4 fundamental forces, and they're defined by the linkage, what it links to and what the range is. When you say the force is universal, that is universal linkage and long range, it's uniquely Einstein gravity. All other forces will come from them as you relax this property. If you relax A and keep B, you get the Maxwell field. Then you say that you relax B, the short range, and linkage to all massive particles. Massive because of that short range to be respected. That will correspond to your weak force. And finally, relax both. You will have a picture of the, that will be your strong force. A last thing we can, does we have a unified picture? Does this picture suggest something? Let's say this. Anything that participates in weak force must have a mass. So that is prediction that the neutrino must have a non-zero mass. Then there are duality relations. The weak and the electric are complementary to each other. Similarly, the gravity and the strong are complementary to each other. So in some relevant space-time, I think someday these dualities should be fully established. Let's stop here. Thank you.
Okay, thank you very much, Professor Dadich. The talk is open for questions. I don't see any hands raised for questions. So I think we thank Professor Dadich again. And I'd like to thank all the speakers of this session for their interesting talks and sticking to the time. And with this, I'll hand the floor back to Professor Alok Mishra.
Thank you, Professor Jain, and thanks to all the speakers, and also thanks to Professor Dadich for accommodating a goof up that I made. Thank you. You accommodated that very graciously. So that brings us to the conclusion of the meeting component of this A.N. Mitra Memorial Meeting and Lecture. So the second post-lunch session is the second component of this, let's call it, for want of a better word, still a meeting, and that would be the A.N. Mitra Memorial Lecture. So we remind ourselves that the first A.N. Mitra Memorial Lecture was given by Professor Panchmakeshan. And in fact, I and my wife were actually there to attend the lecture. It was a very nice experience. I unfortunately am one of those folks who have never formally entered the hallowed stage, so to say, of the Delhi University campus as a student, formally as a student. So sitting on one of those benches way up there was very nice. And so in that same series, we are now going to be doing two things. We are going to be all logging out from this Zoom meeting link. And then we're going to be, I'd request us to please log into the final Zoom link, which is Zoom link number 5 for the second A.N. Mitra Memorial Lecture to be given by Professor Edward Witten. And that is happening at 6:30, 6:6 baje, in about 28 or 29 minutes from now. So let us take a little short coffee break or any kind of break that we want. And let's try to reconvene in about 20 minutes from now. So thank you so very much to everybody. So namaskar.
Thank you. Thank you very much.
So I'm ending the meeting for all now. See you soon on the last Zoom link.